Hello everyone, this is Mr. Fawcett and we are back for part 2 of our lesson on infinite limits. Today's lesson is going to be focused mostly on going through a couple of practice problems, and then we're going to talk about the calculus justification for when a function has a vertical asymptote. So kind of getting away from that pre-calc algebra 2 definition we had and moving into something calculus based. We're going to go to the bottom of the second page, and we're going to do problems 3, 4, and 5. However, I encourage you to try these problems on your own before you come back and look at the explanations and solutions. Test them out. There's a couple different ways you can do these. You can use your TI-84s to make a graph, look at a table. But before you do that, I'd like for you to try to find out where the vertical asymptote is analytically, so without using a calculator. And then you're also trying to figure out what the infinite limit is at that vertical asymptote. So is the function approaching positive infinity? Is it approaching negative infinity? Or if the one-sided limits are approaching different infinities, then the limit would not exist. So take a few minutes to work on those, then click play on the video and see how you did. Alright, so just like I asked you to do, I am going to work out these problems analytically, and then we're going to check our solutions with a graphing calculator. We'll look at both the graph and the table. So right away we should be able to see that this function is going to have a vertical asymptote at x equals -4, because that's where the denominator is going to be equal to 0. And the numerator will not be equal to 0, so we don't have an indeterminate form. But we need to figure out what the limit is as the function approaches that vertical asymptote, so as it approaches -4. So we need to look at both the one-sided limits. So the limit as x approaches -4 from the left-hand side or the negative side. And to do this, remember, we can think about the sign of the function, right? In this case, the numerator is always going to be positive, regardless of what x is. And if we're approaching -4 from the negative side, right? So that's going to be numbers like -4.1, -4.05, etc., which is going to make our denominator negative. And one way you can do that if you can't do that in your head, is just to test a number right to the left of -4. So we can just test, and we can do 3 over -4.1 plus 4. That's going to give us 3 over -0.1, which is going to give us -30. Okay, and again, you're not saying that these two expressions are equal. That's why I don't have an equal sign right here. We're merely testing to see what the sign of the denominator is going to be. Okay, so if the numerator is positive and the denominator is negative, then the limit from the left-hand side is going to be going to -infinity. Now we also need to check the limit as the function approaches from the right-hand side. So we'll do that in red. So the limit as x approaches -4 from the right-hand side or the positive side of 3 divided by the quantity x plus 4. Now, we can do the same thing. We need to think about the signs. So the numerator is always positive. If we are looking at numbers to the right of -4, that's going to be numbers like -3.9, -3.99, -3.999, etc. If it's not obvious to you what sign the denominator is going to be, just check it. Okay, so if I substitute in -3.9, that's going to give me 3 over 0.1, which is going to give me 30. So we're going to, this function is going to be approaching positive infinity from the right-hand side. So right away, if our function's approaching different infinities from both sides, if both one-sided limits are not equal, then we can say that this limit does not exist, right? Because the two one-sided limits are not equivalent. But again, feel free to check your work. Sometimes you may have access to a calculator on the AP exam for these types of questions. Sometimes you may not. So it's good to know how to do it analytically, but it's also good to be able to check your work with a calculator. So let's head over to the calculator software. I'm going to erase this work real quick. Okay, I have already plugged the function into my calculator. First thing we're going to do is we're going to graph it. And we can clearly see that we have a vertical asymptote at x equals -4. But we can also see that as the function approaches from the left-hand side, it's going to -infinity. And as we approach from the right-hand side, it's going to +infinity. So just like we found out working the function out analytically. And then, of course, this limit would not exist. Now, we could try to understand this using a table. So that's what we're going to look at next. So I have my function. I'm going to start my table just to the left of -4. And I'm going to have it increasing by thousandths. Then go to second graph, pull up your table. And you can see as the function approaches -4 from the left, we are approaching -infinity. Those numbers are decreasing. And as we approach from the right, we are approaching +infinity. Okay, so again, a couple different ways you can check your work, graph or table, but I want you to be familiar with both of those methods as well as trying to work out the limit analytically. Okay, let's go and look at number 4. All right, so we have the limit as x approaches 3 of 2 divided by the square of x minus 3. So again, we're going to have that vertical asymptote at x equals 3, and we need to check what the function's doing as we approach from either side. So the limit as x approaches 3 from the negative side. And this one should be a bit more clear than number 3. Our numerator is always going to be positive regardless of what x is, and our denominator also has to be positive, right? And maybe if you're unsure of why that is, take 5 or 10 seconds to think. Okay, our denominator is being squared, right? So if I square any number, I'm always going to get a positive number. So regardless of what we substitute in for x, this one-sided limit is going to be equal to +infinity. And I can check the limit as we approach from the right-hand side, or the positive side. And again, nothing's going to change here. It doesn't matter what I substitute in for x. My numerator is always positive. My denominator is always positive. So I am going to approach +infinity. Since both my one-sided limits are the same, that means that my regular limit is going to exist, and it's going to be +infinity. Okay, so now we're going to check our work with a calculator. Okay, so I've entered the function. We'll first check out the graph. We can see that there is that vertical asymptote at x equals 3. Uh-oh. Give me 1 second. Okay, so we have that vertical asymptote at x equals 3. And this time we can see that the function is approaching +infinity from both sides. Again, just what we worked out analytically. So the limit at x equals 3, or the limit as a function approaches x equals 3 would be equal to +infinity. Let's check the table though. Another representation. I have already entered where I want to start my table at, just to the left of 3. I'm going to increase by 1,000th again. So then second graph. And this looks a little different than what we may have seen before, but as the function approaches 3, we can see that these numbers are increasing. Now, if the calculator runs out of digits, we just see this e to the 6. And that just means we're multiplying 2 by 10 to the power of 6. So this equals 2 times 10 to the power of 6. Again, they're just rewriting it because to save space, essentially. They don't have enough space in the calculator to write all those digits, so they shorten it using a form of scientific notation. As we approach, so we approach infinity as we approach from the left, and as we approach from the right, we can also see that these numbers are increasing, just like they were when we approach from the left. So our limit as x approaches 3 is positive infinity. All right, we are going to head back, and we are going to look at number 5 to finish off our set of 3 practice problems. Now, number 5 has a trig function in it, which is good because numbers 3 and 4 didn't, and it's a little bit trickier when we think of the one-sided limits. So right off the bat, we should see that this function is going to have a vertical asymptote at x equals 0 because sine of 0 is 0, which means we have a non-zero number in our numerator and a 0 in our denominator. So we're going to get a vertical asymptote. Now let's take a look at the one-sided limits. We'll do the limit as x approaches from the left-hand side first. And the way we thought about the previous 2 problems is if I substitute in a number to the left of 0, so something like sine of negative 0.1, we could see what the sign of our denominator is. No pun intended. I know we're talking about a sine function, but I'm talking about the sign as far as positive or negative goes. And look at the sign of the numerator to see which infinity we are approaching. However, it may not be clear what the sign of negative 0.1 is. So let's pull out a unit circle, and maybe that'll bring back some memories from pre-calc and algebra 2. So our unit circle, let me put some axes on here. Our unit circle is a visual representation of the sine and cosine values for different angle measurements. So we're looking at the angle from the x-axis. So as I travel along the unit circle this way, how many radians, because you can do radians or degrees, but we're going to talk about radians. It's how many radians have I traveled? So what angle have I traveled? If I haven't gone anywhere, right, well, I'm going to be at 0 pi radians. If I've gone a quarter away along the circle, I'm going to be at pi over 2 radians. If I've gone if I've gone halfway, I'll be at pi radians, and 3/4 will be 3 pi over 2 radians. If I travel all the way around, one complete rotation, we know that should be 2 pi radians. So if I pick a point on the unit circle, oops, I still have my eraser on. Let's go back, put our axes. Oh, still have the eraser on. Let's try one more time. All right, x and y axis. All right, now let's pick a point. So if I pick this point right here, I'm going to say that this has an angle of pi over 6. So all that means is that I've traveled pi over 6 radians along the unit circle. Now I could pick a point below the x-axis. Okay, and I'll say I'm going the same distance, just in the opposite direction. So this would be negative pi over 6 radians. But now we need to figure out where our sine and cosine comes in. So if I think about the ordered pair for this point, right, my x value is going to be the cosine of our angle. So the cosine of pi over 6, my y value is going to be the sine of that angle, so sine of pi over 6, and same thing down below. So my x value is cosine of negative pi over 6, my y value is sine of negative pi over 6. So if we go back to our original problem, we're trying to figure out the value of sine of an angle that's slightly less than 0. So in this case, we could look at the negative pi over 6 angle because that's slightly less than 0. And if we look at the quadrant that this point is in, so this point is in the 4th quadrant, which means my x values are positive and my y values are negative. Now, since my sine values represent my y values, I'm going to be looking at my y values. And we just said our y values are negative, which means my sine value is also going to be negative. Now, you don't have to know the exact sine value of negative pi over 6. It turns out that it's negative 1/2. But again, if you just know the quadrant, you'd still be able to figure this limit out. So if my numerator, 4, is positive, and my denominator is going to be negative, that's going to give me a limit that is approaching negative infinity. And I could do the same thing as we approach from the other side. So the limit as x approaches 0 from the positive side. Now I just want to think about an angle measurement that is slightly greater than 0. So why not use pi over 6? Okay, again, my cosine values represent the x values, my y values represent my sine values represent my y values. And we're in the 1st quadrant, so my y values are going to be positive. So the sine of 4 is always positive. The sine of my sine values is always going to be positive. So this limit, right, is going to approach positive infinity. And since my two one-sided limits are different, that means my actual limit is not going to exist, D and E. So hopefully that was a good refresher about the unit circle and how we can figure out what sine and cosine values we have based on what the angle is. We're not going to check this in the calculator for sake of time. However, I do encourage you to pause the video and do that yourself just to get more practice with graphing and finding values from tables. The last thing we're going to finish with today is we're going to go to the last page and look at the calculus justification of a function having a vertical asymptote at a certain x value using limits. Okay, so I just put the justification up here for you, and then we're going to read it together. It says x equals a, so that, again, x equals any number is just going to be a vertical line, is a vertical asymptote of f of x if and only if the limit as x approaches a from the negative side of f of x is equal to positive or negative infinity, or the limit as x approaches a from the positive side of f of x is equal to positive or negative infinity. So essentially, you can prove that there is a vertical asymptote of a function at a specific value if either of the one-sided limits approach positive or negative infinity. So again, this is our calculus justification. In pre-calc, you may have justified a vertical asymptote by saying that the denominator was equal to the denominator of a function was equal to 0, and the numerator was equal to some other number than 0. But now we're looking at how could we justify this using calculus. You may wonder why only one of these limits has to approach positive or negative infinity for us to have a vertical asymptote, and you might think, well, why don't both of them have to approach one of the infinities? Well, let me leave you with this example to show you why. Let's say that I have a vertical asymptote at x equals 3. And let's say the left side as my function approaches 3 from the left-hand side, looks something like this. So that approaches positive infinity. But from my right-hand side, I have something that looks like this. right? This function does have a vertical asymptote at x equals 3, but only one of the one-sided limits approaches infinity. However, it still fits all the characteristics of what a vertical asymptote is, right? The function doesn't cross or touch the vertical line x equals 3, which makes it a vertical asymptote. Okay, hope you enjoyed this video, found it informative. I would encourage you to finish the rest of the practice problems in this packet, and of course, come to me with any questions or concerns. All right, this is Mr. Fawcett. Enjoy the rest of your day.